Okay, welcome to metallic bonding. In this video, we're going to go through what a metal is. We are going to go and look at how metals are bonded to each other, and we're going to reference a few things that we've learned about ionic bonding and covalent bonding. Let's get straight into it. Okay, so over here we've got this is a sodium atom. We know this is in group 1. We know this is a metal. Okay. We know that sodium also, because it's in group 1, it has one electron, okay, in its outer shell that it normally would give over to another atom. Okay, but in this case, we've got a whole bunch. I've taken this sodium atom and I've put a whole bunch of them together. And what happens is in this example, these electrons from the sodium, so this one over here, just keep imagining that there's that minus there. This electron is now free to flow in between other atoms of sodium. Okay, so we say that if it's not belonging to a particular atom, then we say that it is a delocalized electron. Delocalized means it doesn't hold on to a particular atom. So delocalized electron. Okay, I'm just putting some keywords over here that I mentioned. All right, so of course, you know, we've just got this one electron from this one sodium atom over here. It's got this positive nucleus. We know this already. Now, of course, we're going to have a whole bunch of these electrons from all the other sodium atoms. So I'm just sort of throwing these in now. And these electrons, we say, move freely within this metal. Okay, so let's go ahead and put little minuses on them so that we know that these are electrons. They're negatively charged. So we say a delocalized electron. We sometimes also refer to this as a sea of electrons, because these electrons are flowing and moving about. We sometimes refer to them as delocalized electrons or delocalized sea of electrons, which is what I've seen. So this is what is effectively what a metal looks like. And this particular arrangement, the sea of electrons with these sodium atoms, is what gives metals their properties. And we're going to get into that a little bit later. So let's just find out what is exactly holding these electrons, not electrons. What is holding these sodium atoms together? And it's the idea that there is this electrostatic force of attraction. Remember this word before, electrostatic force of attraction between these components. So we've got this very positively charged sodium atom that's lost an electron. It's become this positive charge. It's then created this this force of attraction, electrostatic attraction, to this one delocalized electron. Same thing's happening here with this one. They're all this force of attraction between 4 of these sodium ions. They're ions because they've lost one of their electrons. And it's this force of attraction that gives metals its very hard, solid characteristic. Now, because sodium has only one electron in its outer shell, so we've got one electron, we're working with sodium here, sodium generally isn't that hard. And it's for this reason that you don't really have that many strong forces of attraction, because there's only one electron. Now, if you go on to magnesium, or if you go on to any other of the metals in group 2, there's more electrons, which means there's more electrostatic force, which means it's going to be harder. Okay, it's going to be a harder metal. It's also going to have a higher melting point. This is another physical property that we always talk about with metals. So it's got a higher melting point because it's got more electrostatic force. You need more energy to then overcome those forces. So high melting point. This, of course, is not true for sodium because there aren't that many forces of attraction. Well, there are forces of attraction, but they're just not that strong. Okay, so that's the electrostatics of metallic bonding, and that's the sort of reason why, if we go back to this image, the reason why these sodium ions are sort of glued together. Okay, so let's go on and talk about the physical properties of metals, like we've just mentioned. So metals, as we know, they conduct electricity. Whoopsie, that's supposed to be a arrow. So they conduct electricity, and we know this. And what is electricity? Well, electricity is the flow of electrons, right? And what we know is we've got a sea of electrons. So if I just drew the sea of electrons in this sort of wire over here. Okay, so this wire, I mean, generally electrical wire is generally made of copper, which is a metal, and remember, metals are going to have these ions, these positive ions, and then they're going to have the sea of electrons. And it's the idea that there is the sea of electrons that allows the electrons that are coming out of the negative terminal of the battery to then flow in between these positive ions, to flow through the wire. I've just enlarged the wire, then leave out through this section, go through the light bulb, and then come back to join the circuit. So as soon as these electrons have left this section, they are going to be replaced by electrons coming out of our source of energy, our battery. Okay, so this is the sort of movement of electrons through a metal, and it's the idea that we have a sea of delocalized electrons that allows this property to happen in a metal. So they conduct electricity. So this is one of the properties of metals. Of course, we have another property of metal, which is, or another two properties of metals, is that they are malleable and they are ductile. No matter how much we move these ions. So if I had to sort of knock this ion to the right over here, which is not allowing me to do that. Okay, let's just say we moved that ion to this position. It's still going to have a electrostatic force of attraction between that ion and that electron. Okay, so that's the reason why metals are able to sort of bend into shapes that we want them to bend into if we hammer them or if we bend them. It's because the force of attraction still exists between the ions. So this example here, if I shifted all these ions to the right, and I eventually ended up with this picture here, we're still going to have the forces of attraction between those delocalized electrons and those positive ions of this particular metal. Okay, so we're able to stretch metals out. This is what ductile means, is you're able to stretch them into wires, and they are malleable. We are able to bend them without breaking, and it's because of this reason, of this force of attraction between these particles, is the reason why we have this property for metals. Excellent. So I hope that's been really helpful, and nice short one here on metals and metallic bonding. Excellent.